Welcome. In this video, we'll explore two important C++ concepts, using constcast and mastering exception handling. We'll start by understanding how constcast works, then move on to the essentials of exception handling, including standard and user-defined exceptions. By the end, you'll have a solid grasp of these powerful C++ features and how they can make your code safer and more flexible. Let's dive in and begin with constcast, a tool that allows you to modify the constness of pointers or references in your code. Constcast operator in C++ is used to add or remove the const qualifier from a variable. This can be useful when you need to pass a const pointer to a function that requires a non-const pointer, but you must use it with caution. Modifying a truly constant value leads to undefined behavior, so constcast should only be used when you are certain the object was not originally declared as const. Let's see how this works in practice with a simple example. Consider this program. We declare a const integer variable and a pointer to it. Using constcast, we remove the constness from the pointer, allowing us to pass it to a function that expects a non-const pointer. The function multiplies the value by 10 and returns the result. This demonstrates how constcast can be used to interact with functions that require non-const pointers, but remember, modifying the original const variable is not safe. When we run the program, the output is the value of ptrcast 500. This confirms that the function received the pointer, dereferenced it, and multiplied the value by 10. The key takeaway is that constcast allows you to work around const restrictions in specific scenarios, but always be careful not to modify truly constant data. Now let's shift gears and talk about exception handling in C++. Exceptions are problems that arise during program execution, such as dividing by zero. Exception handling provides a way to transfer control from one part of a program to another when an error occurs, making your code more robust and easier to debug. C++ exception handling is built on three main keywords: try, catch, and throw. The try block contains code that might throw an exception. If an error occurs, the throw statement is used to signal the exception. The catch block then handles the exception. This structure allows you to separate error handling code from regular logic, making your programs cleaner and more reliable. Typical try-catch block looks like this. You wrap the code that might cause an error inside a try block. If an exception is thrown, one of the following catch blocks will handle it, depending on the exception type. You can have multiple catch blocks to handle different types of exceptions, making your error handling flexible and precise. You can throw exceptions anywhere in your code using the throw statement. The type of the thrown value determines which catch block will handle it. For example, if you throw a string when a division by zero occurs, only a catch block designed to handle strings will catch it. This mechanism helps you handle different error types appropriately. After a throw, the nearest matching catch block is executed. You specify the type of exception you want to catch in parentheses after the catch keyword. If no matching catch block is found, the program may terminate. To handle any exception type, you can use a catch block with an ellipsis catch, which acts as a catch-all handler. Let's look at a simple example. We declare an integer with a value of -1. Inside a try block, we check if x is less than 0. If so, we throw. The catch block for int catches the exception and prints a message. The output shows the flow before try, inside try, exception caught, and after catch. This illustrates how control moves when an exception is thrown and caught. Sometimes you may not know what type of exception will be thrown. In such cases, you can use a catch-all block, catch. This block will catch any exception not handled by previous catch blocks. For example, if a float is thrown but only int and char catch blocks exist, the catch-all block will handle it, ensuring your program doesn't crash unexpectedly. It's important to note that C++ does not perform implicit type conversion for exceptions. For example, if you throw a char but only have a catch block for int, the exception won't be caught by that block. Instead, it will be caught by a catch-all block if one exists. Always ensure you have catch blocks for the specific types you expect to throw. C++ allows you to nest try-catch blocks. You can also rethrow an exception using the throw statement. This is useful when you want to handle part of an exception in one block and pass it up to another handler. For example, an inner catch block can handle some logic, then rethrow the exception for the outer block to finish handling. When an exception is thrown, all objects created inside the enclosing try block are destroyed before control is transferred to the catch block. This ensures proper cleanup and prevents resource leaks. For example, if you create an object inside a try block and then throw an exception, the object's destructor will be called automatically. Here's a practical example. We define a division function that throws an exception if the denominator is 0. In main, we try to divide 50 by 0. The division function throws a const char asterisk exception which is caught in the catch block. The program prints an error message instead of crashing, demonstrating safe error handling. In catching exceptions, it's important to match the type thrown. In the division example, we throw a const char and catch it with a catch block for const char asterisk. If you use a different type, the exception won't be caught and the program may terminate. Always ensure your catch blocks match the types you throw. C++ provides a set of standard exceptions defined in the exception header. These exceptions are organized in a hierarchy with std, exception as the base class. Derived classes include bad alloc, bad cast, logic error, and runtime error, among others. Using these standard exceptions helps you write more consistent and maintainable code. The std, bad alloc exception is thrown when memory allocation with new fails. This is one of the most common standard exceptions. It inherits from std exception and provides a what method that returns a description of the error. Catching bad alloc allows you to handle memory allocation failures gracefully. In this example, we try to allocate a very large array using new. If the allocation fails, a bad alloc exception is thrown. The catch block for bad alloc catches the exception and prints the error message using the what method. This prevents the program from crashing and allows you to handle the error appropriately. The std out-of-range exception is thrown when you try to access an element outside the valid range of a container, such as a vector. This helps you catch errors like accessing an index that doesn't exist, making your code safer and easier to debug. Here, we create a vector with 2 elements and try to access the 6th element using the at method. Since this index is out of range, an out-of-range exception is thrown. The catch block catches the exception and prints an error message, including details from the what method. You can define your own exceptions by inheriting from the std exception class and overriding the what method. This allows you to create meaningful error messages and handle specific error conditions unique to your application. In this example, we define a myException class that inherits from std exception. The what method returns a custom error message. In main, we throw an instance of myException and catch it, printing both a custom message and the result of what. This demonstrates how to create and use user-defined exceptions in C++. Let's see another user-defined exception example. We create a myException class that returns a message for division by 0. In main, we prompt the user for 2 numbers. If the second number is 0, we throw myException. The catch block prints the error message, ensuring the user is informed about the invalid operation. C++ allows you to specify which exceptions a function might throw using the throw specifier. For example, float my function char param throw int means the function can only throw int exceptions. If it throws a different type, it won't be caught by a regular int type handler. This helps document and control exception behavior in your code. If you declare a function with an empty throw specifier like int my function int param throw, it means the function is not allowed to throw any exceptions. This can help enforce stricter error handling and prevent unexpected exceptions from escaping your functions. Functions without a throw specifier can throw exceptions of any type. This is the default behavior in C++. While this offers flexibility, it also means you need to be careful and ensure you have appropriate catch blocks to handle any exceptions that might be thrown. When using exceptions, always catch exceptions by reference to avoid unnecessary copying. Use specific catch blocks for known exception types and a catch-all block for unexpected errors. Clean up resources in destructors or use smart pointers to prevent memory leaks when exceptions occur. Standard exception hierarchy in C++ starts with std exception at the top. Derived classes include logic error and runtime error, each with their own subclasses for specific error types. Understanding this hierarchy helps you choose the right exception type for your needs and write more maintainable code. Logic errors, such as domain error or invalid argument, can often be detected by reading the code. Runtime errors like overflow error or out of range occur during program execution and are harder to predict. Handling both types of errors with exceptions makes your programs more robust. A domain error is thrown when a mathematically invalid domain is used, such as taking the square root of a negative number. Catching domain error exceptions allows you to handle these cases gracefully and provide meaningful feedback to users. The invalid argument exception is thrown when a function receives an argument that is not valid. For example, passing a negative number to a function that expects only positive values. Catching this exception helps you validate input and prevent incorrect operations. A length error exception is thrown when you try to create a container like a string or vector that exceeds its maximum allowed size. This helps prevent memory issues and keeps your program stable even when handling large data sets. The out-of-range exception, as seen earlier, is thrown when accessing an invalid index in a container. Always use methods like at instead of operator when you want bounds checking and automatic exception handling. The runtime error exception is used for errors that cannot be detected by reading the code, such as hardware failures or unexpected runtime conditions. Catching runtime error helps you handle these unpredictable situations and keep your program running smoothly. Overflow error and underflow error exceptions are thrown when mathematical operations exceed the limits of the data type. For example, adding 2 large integers might cause an overflow. Catching these exceptions helps you detect and handle such errors before they cause incorrect results. A range error exception is thrown when you try to store a value that is out of the valid range for a data type. This helps you catch and handle errors related to data limits, ensuring your program doesn't produce invalid results. Is thrown when a mathematical operation results in a value too small for the data type to represent. Catching this exception allows you to handle precision issues and prevent incorrect calculations in your programs. In real-world applications, exception handling is essential for building reliable software. By anticipating possible errors and handling them gracefully, you can prevent crashes, provide helpful error messages, and ensure a better user experience. Always plan for exceptions, especially when dealing with user input, file operations, or network communication. To recap, we've covered how to use constcast to modify pointer constness, the basics of exception handling in C++, standard and user-defined exceptions, and best practices for writing robust code. Understanding these concepts will help you write safer, more maintainable C++ programs. Here are some practical tips. Always use specific exception types when possible, clean up resources in destructors, and avoid using exceptions for normal control flow. Use standard exceptions for common errors and define custom exceptions for application-specific cases. Avoid catching exceptions by value as this can lead to object slicing. Don't ignore exceptions, always handle them or let them propagate to a higher level. Also, avoid throwing exceptions from destructors as this can cause program termination if another exception is active. For advanced scenarios, consider using exception specifications and noexcept for functions that should not throw. Use smart pointers to manage resources automatically and leverage the full hierarchy of standard exceptions for precise error handling. Test your code for exception safety by simulating errors and ensuring resources are properly cleaned up. Use unit tests to verify that exceptions are thrown and caught as expected and that your program remains stable under error conditions. Congratulations! You've learned about constcast, exception handling, standard and custom exceptions, and best practices in C++. Continue practicing these concepts in your own projects and explore more advanced features like noexcept and smart pointers to further enhance your C++ skills.